Let's look at this function. F of x, y equals y squared over x. Look at that pen, it writes so nicely. At the point 2, 4, 8. You could also just be given the point 2, 4 and be expected to find the function value was 8. So we want to find the directional derivative at p in the direction of 2, 1. All right, well, we know how to find directional derivatives. It's going to be the gradient of f dotted with the normalized vector u. I should say the gradient of f at the point 2, 4, dotted with the vector u, or really u divided by its own magnitude. Okay, so let's write down the things. The gradient of f, I'm doing this in a strange way, but already I started that way. Okay. So the gradient of f is going to be the partial with respect to x, partial with respect to y. It's going to be, let's see, so I might want to rewrite my function. I think it's a good idea to rewrite this as x to the -1 times y squared. It's going to make it easier. I don't want to use the quotient rule, right? That seems terrible. So the partial with respect to x is going to be -x to the -2 times y squared. And the partial with respect to y is going to be x to the -1 times 2y. And if you prefer, although you certainly don't have to, you could rewrite this as -y squared over x squared and 2y over x. I don't think you need to do that, but you certainly can. And then we're going to specifically plug in the point that we're given. So the gradient evaluated at the point 2, 4 is going to be, let's see, -4 squared over, oops, sorry. Let me do the one thing too. I always forget to do this where you're like, just click on this and then this part. Yeah, that's better. Okay, much better. So -4 squared over 2 squared, and then it's going to be 2 times 4 over 2. Thanks. So let's see, that's going to be -16 over 4. Oh, that's interesting. Also, I do have solutions here. I just want to make sure I'm not making dumb mistakes because it feels like, I don't know, it just feels wrong to me. Not for any good reason other than just kind of thought it was going to be different, but no, it's totally right. It's good to be like. And then we should also find our u divided by its own magnitude. So that's going to be, well, u is the vector. Oh, did I write down what u was? I did not. I thought I did. No, I really didn't. I said it. I said, or maybe I didn't. We were doing the directional derivative at this point in the direction of 2, 1. So the vector divided by its own magnitude should be 2, 1 divided by what? What is the magnitude of that vector? How much? Yeah, square root of 5. Square root of 2 squared plus 1 squared. Finding the magnitude of a vector should be very, very straightforward. Maybe the calculation is less nice than this, but it's really a straightforward process. And then we do the thing. We say, okay, well, I'm going to do my directional derivative. It's going to be my gradient, which is -4, 4, dotted with this direction vector divided by its magnitude. Whoops, I don't need that there, sorry. Which is going to be, let's see, -4 times 2 plus 4 times 1 times 1 over root 5. Welcome, thanks. So simplifying this, let's say I get -8 plus 4, so that's going to be -4 over root 5. And I would probably leave it like that. I suppose you could rationalize it as -4 root 5 all over 5, but I don't think anyone really cares if you rationalize it or not. Come on in. It's going over the Thanks. The midterm one review. How did I get root 5? Sure. So the magnitude of u, if u is equal to the vector 2, 1, the magnitude of u is the square root of 2 squared plus 1 squared, which is the square root of 5. That's how we're getting square root of 5 there. Other questions about it? This one. We've got more to do with this one, but yeah. So find the maximum rate of change of f of x, y at the point P and the direction in which it occurs. Okay. So the maximum rate of change of f of x, y at P. There's a very, very simple answer to this question. It's going to take a little bit. Well, actually, it's not going to take that much work at all, actually. The maximum rate of change of a function at a point is the magnitude of the gradient evaluated at that point. That's it. So if anyone ever asks what's the maximum rate of change at a point, it's the magnitude of the gradient. Or as I like to say, the gradient is always the direction of the steepest increase. So if they want to know what the steepest increase is, it's just the magnitude of the gradient. Well, we've already found the gradient before, right? We know that that's going to be the magnitude of the vector negative 4, 4. Right? That is the gradient at the point 2, 4, 8. We did that work in the previous problem, right? There's the gradient right there at the point 2, 4, which is what P is. Okay. And so we know how to find magnitude. It's going to be the square root of negative 4 squared plus 4 squared, which is going to be the square root of 16 plus 16, which is the square root of 32. And you might simplify that as 4 root 2. I wouldn't worry. So like, I wouldn't do that, really, unless someone specifically is saying simplify as much as possible or whatever, which they might. But I would, if I was taking this test, I would leave it like that. And if I had all the time in the world at the end, I would come back and do that. Maybe. But the issue with this is, 1, it takes time. 2, you might make a mistake. Doing this is just an opportunity to lose points if you're not being asked to do it. If you're not being asked to simplify or to make something rational or whatever, leave it alone. Okay. So, oh, and then they also ask the direction in which it occurs. So what is the direction of the maximum rate of change? Everybody should be able to say very generally what that is. It's the what? What direction is the maximum rate of change? Starts with a G, ends with an gradient. It's the gradient. The gradient is always the direction of the maximum rate of change. But here's what I want to make extra clear. It's probably going to be the case that this is probably not the answer. Why is it not the answer? Because it's not a unit vector. So when someone says direction, even if they haven't been specific, they probably mean I want your vector and your vector and your vector and your vector and your vector to all look the same. I don't want you to say negative 4, 4, and you to say negative 2, 2, and you to say negative 1, 1. I want everyone to give me the same vector. And to make sure that happens, we say we have to normalize them or make them all unit vectors. So we're going to normalize it. So you're just going to take the gradient vector and divide by the magnitude that we already found. That's why it's good to do the magnitude first, because we already found it. So the gradient vector, the gradient vector divided by its magnitude is just negative 4, 4 divided by 1/4√2. This probably is a place where it probably is a good idea to have done the simplification. So maybe I have to take back what I said over here. We could leave it like that, or we could distribute and say it's -4/4√2, 4/4√2, and then cancel some 4s to get -1/√2. So there is the direction of the maximum rate of change. And it is a unit vector. Its magnitude is 1. So I want you to really make that stick in your head. Someone says, what's the direction of the maximum rate of change? It's the direction of the gradient vector. If someone says, what is the maximum rate of change? It's the magnitude of the gradient vector. No, you don't have to do any other justification. You're entitled to know that information. Questions? And while you're certainly welcome to take pictures, I will post this on Google Drive as well. So again, totally fine if you want to take pictures. I don't mind at all. But just so you know, I will also post the notes on Google Drive later today after class. So, part C. In what direction does the function decrease most rapidly at P? So direction of most rapid decrease. Well, if the function's getting the biggest, the fastest in that direction, the function is getting the smallest, the fastest in that direction, the opposite direction. So literally, if you've answered part B, the answer to part C is just change the signs. So it is going to be negative the gradient divided by its own magnitude, which is just negative 1/√2, 1/√2, which is just, I would distribute the minus sign. That's it. Sorry, I can't see that. Sure, yes, definitely. So there's two things to know about the gradient, really. So thing one, the gradient itself, and usually we want to normalize it, so we divide by its own magnitude. But the gradient vector is the direction, bless you, of the maximal rate of change. Or in other words, in this direction, the derivative is the biggest, the most positive it can be. And then, to go along with that, the words. What's that called? When you take the thingy? Oh my God, it's the magnitude. I'm like, there's a thing there. It's the magnitude. The magnitude of the gradient is the maximal rate of change. Those are the two things, really. I mean, there's other things to know about the gradient, but like those are kind of the things you want to know. Can you not see it? Yeah, because I did the paper the other way. I guess I could zoom out a tiny bit. Sorry, I just did the thing and then undid the thing. Nope, nope. Paper is too big. There we go. At the very bottom there. Okay. Paper is killing. Oh, what? Oh, the paper pushed up the on/off button and turned it off. That was really great. Sorry about that. Like, why am I big all of a sudden? There we go. Maybe I should orient the paper horizontally. That might make more sense, like I usually do. Or as we say, what, landscape? Sure, yeah, landscape. Let's go landscape. And then this portrait garbage. Okay. So let's, all right. So part D, actually, this is excellent. Now I can see the questions better too. Find the linearization of f of xy at P. Linearization of f of xy at P. So this is probably something, I don't know if you're being given this or not. The definitions, or you mean like the ones I just wrote? Like these ones here? Is that what you're talking about? Hopefully that's what you want. I'll leave those up there. Okay, cool. So the linearization of a function at P, L of xy is going to be f of the point. Let's call the point x naught, y naught for the moment. Plus, then it's the partial with respect to x times x minus x naught, plus the partial with respect to y, evaluated at the point times y minus y naught. And luckily, we already have most of those things from our previous work. So look back at the first page here. Let's see. We have fx, we have fy. Great. So, in fact, we have them evaluated. So one thing to keep in mind when you're taking a test is don't repeat your work if you don't need to, right? Like I was about to go find the partial again of fx and fy, but I don't really need to do that. I've got them right there, and I've even plugged in the values. So I know that this part here should be -4. And this part here should be +4. And this part here should be what? My favorite number. It's 8. I know it's 8. It's 8 because that's what the function value is, right? They told us that we're evaluating this at the point 2, 4, 8. X is 2, y is 4, and the function value is 8. So don't do more work than you have to do. And then we want to use it to approximate f of 2.1, 3.8. So let's write this out. We've got our linearization is 8 minus 4 times x minus x naught is 2. I'll show you guys can see that. Plus 4 times y minus y naught is 4. There's our linearization. You should not simplify this further. You certainly could make it like, I mean, if you simplify this further, it would look like, I don't know, 6, okay, that's lame, fine. It would look like -4x plus 4y, but I'm going to tell you, it's easier to plug in 2.1, 3.8 to this. Right, 2.1 minus 2 is easy. And 3.8 minus 4 is easy. I don't want to multiply 3.8 by 4. And then, right, that's not what I want to do. You want to do the subtracting before you do the multiplying. So I'm going to have 8 minus 4 times 0.1 plus 4 times -0.2. That's going to be 8 minus 0.4. Sorry. No, that's right. Yeah, I feel like I was like, usually you'd have a plus sign there, but there's a minus because the fx was negative. And then minus another 0.8. So that's going to be 6.8. So what that means for us is the function evaluated at 2.1, 3.8 can be approximated as 6.8. And, ooh, yeah, some chain rule, right? If x equals t cubed plus sine of t, and y equals e to the 3t plus the natural log of t, sorry, yeah, plus the natural log of t. Use the chain rule to find the derivative of the function with respect to t. So this is the thing where we have to make the little diagram. We know that our function f is a function of x and y. And as a reminder, f is x to the -1 times y squared. And then x and y are both functions of t. So to write down the derivative just as a formula, it's going to be df dt equals del f del x times dx dt plus del f del y times dy dt. All the paths that get us from f to t. Everyone cool with why I was saying del and why I was saying that? That's d. Okay. It's okay if you're not cool. Like I can totally say why. I think everyone's cool. Where do we get the 8 again? So you could have actually done the work, which I didn't, and said, oh, I want f of 2, 4. And remembering that f is this function here, f of 2, 4 is 2 to the negative 1 times 4 squared, or more easily written as 4 squared over 2, which is 16 over 2, which is 8. But what I really did was I just looked at the initial, oh, can you see that? Yeah. I looked at the initial information. I was like, oh yeah, if you plug in 2 and 4, the output value is 8. Okay, oh, sorry, you guys. So now we just have to do all the things. Luckily, we've done this part and this part already. Those are just the partials we've already found. So looking back at the work I did in the first problem, fx is going to be, or del f del x is going to be negative x to the negative second times y squared. And dx dt is what I'm going to have to find. So dx dt is going to be 3t squared plus cosine of t. And then del f del y is going to be x to the negative first times 2y. And then dy dt is going to be e to the 3t times 3 plus 1 over t. And I would probably leave it like that, but you might be asked to actually plug in what x and y are. But if you're not, I would just go done. That's it. But we could, yeah, I really feel like no one should be asking you to plug in x equal to this and y equal to that. That seems onerous. That's it. That's all there is to the problem. Unless you wanted to be like, okay, it's going to be, oh, I don't even really, it makes me hurt just to think about writing this, but right, this is awful. I don't think anyone's asking you to do this, but so here's how you would know you were being asked to do this. They could say find df dt evaluated at t, or del df dt parentheses, right? Oh, then they want you to actually write it as a function of t, and then they would want you to do all this, like that homework problem where they're like find dh dt evaluated at t. That's when you had to plug in everything. Same kind of idea here. So if they didn't ask for that, you would just leave it in terms of x, y, and t. If they did, you would write out the whole dumb thing, which I'm doing now because I started it and I can't stop. Okay, terrible. I'm sorry, you can see that. So that's problem 1. I mean, problem 1 had a lot of parts, but yeah. Yeah.
Oh, what's in the second, like set of
Right here?
no, where it's like e to the 3t plus.
Right here?
No, all the way to the left side.
Here? Sorry, I'm not sure which one you want.
One over, yeah, right there.
E to the 3t plus the natural log of t, which is just what y is. Because, right, I'm replacing the negative x to the negative 2 with negative x to the negative 2 times y squared. There's y squared. And then the same deal over here. I've got x to the negative 1 times 2y times here dx dt, here dy dt. But again, I don't think anyone should be asking you to do it. Not that they couldn't, but it seems not a very good use of test time to ask someone that question. Not what I would be interested in having my students know. All right. Other questions about that one? Okay. Let's look at number 2. Here's number 2. In order to treat a certain bacterial infection, a combination of 2 drugs is being tested. Studies have shown that the duration of the infection can be modeled by the following. So duration is modeled by d of x comma y, x squared plus 2y squared minus 18x minus 24y plus 2xy plus 120, where x is the dose of drug 1 in milligrams, and y is the dose of drug 2, also in milligrams. Oh, sorry. I would say yes. Someone asked the question, do we need to be able to apply the formulas from the textbook for the chain rule where the trees get extremely large? I don't know about extremely large, but certainly probably larger than the one we just did. If we have time at the end, I'll circle back around to that because there are other examples that are a little bit larger, that are a little more complex. I wouldn't say extremely large. I would say tiny bit larger than what we just did should be still reasonable to ask on a test. But we'll come back to that. Let's see. So what dose combination of the drugs will minimize the duration of the infection? So we want to minimize D. Now I'll point out, I don't love the choice of D for the function name because we also use capital D for the thing that we're going to use in this problem, right? D being fxx squared minus fx minus fy minus fxy squared, right? That thing. So I might change the name of my function. I might change it to lowercase d, just because I know I'm going to use uppercase D for something else. So let's minimize the duration, lowercase d. To minimize a function, we have to find the critical points and then see that we get, hopefully we actually get a minimum, right? Notice, right, this isn't a global max or min problem because they didn't give us a domain to work on. Now, something to consider, and hopefully this isn't an issue, but it wouldn't make sense to have a negative amount of a drug in milligrams. So even though they didn't give us a domain, we should at least be thinking about the fact that, oh, well, x probably needs to be greater than or equal to 0. And y probably needs to be greater than or equal to 0. Otherwise, we're going to have problems. Like, I can't give you negative drugs. Take the drugs out of your body. I can't do that. So let's find the gradient and set it equal to 0. Now, really, I never write it as the gradient. Even though that's what we're totally doing, I'm just going to write it as setting fx and fy equal to 0. So fx is going to be 2x minus 18 plus 2y. And fy is going to be 4y minus 24 plus 2x. And you might notice here, it's not particularly easy or possible to solve either one of these independently. There is no just straight value you get for x in this first equation or for y. Sometimes you'll do one of these problems, you'll be like, oh, you'll get x equal to 3, and you plug it into the other part and figure out what y has to be. That's not the case here. So what do? Well, we isolate one of the things. Now, if I was trying to make my life as easy as possible, I would observe that I have a 2x there and a 2x there. So I might make the smart choice of saying, well, I'm going to say 2x has to equal 18 minus 2y. And then I also might make the same choice here and say, oh, 2x has to equal 24 minus 4y. And then it is definitely true that 2x has to equal 2x. No choice about it. 2x is definitely equal to itself. Or in other words, you're going to isolate something, the same thing in each thing, so that you can plug these up and equal to each other. That's not the only way to do it. I'll show you another way in just a second if you don't like this. But one way to go is to say, oh, 18 minus 2y has to equal 24 minus 4y. I'm going to add 4y to the left. I'm going to subtract 18 from the right and get y equal to 3. And then plugging that back in to either place, we either get 2x equal to 18 minus 2 times 3, which gives me 18 minus 6, which is 12. So x equals 6. And if you plug it in there, you'll get the same thing. 24 minus 12 is 12, and 12 divided by 2 is 6. Well, let's say you don't love this, and I get not loving it. I'm always trying to look for the easiest path, and sometimes it's not always the easiest path to see. So probably a more natural way of doing this might be to say, I'm going to solve one of these things for y. So 2y equals negative 2x plus 18, and then divide by 2. And then throw that into the other equation. So then I'm going to have 4 times negative x plus 9 minus 24 plus 2x equal to 0. So negative 4x plus 36 minus 24 plus 2x equals 0. That's a negative 4x plus a 2x, so a negative 2x. 36 minus 24 is 12. So 12 equals 2x, so x equals 6. If x equals 6, y equals 3. Same thing either way, whichever way is more. So basically, you're trying to find the simultaneous solution to these two equations the easiest way possible. And I should be more general, the simultaneous solutions, plural, right? Because there could be more than one critical point. We only got one here, and luckily it makes sense, right? Both x and y are positive. But we need to now check and see it's a minimum. Now, hopefully no one asks you a question to find a minimum and then there isn't one. If they say find the minimum, there should be a minimum. But let's check. I need to find capital D, which is fxx times fyy minus fxy quantity squared. So let's see. There's fx equal to 2x minus 18 plus 2y. So fxx is going to be 2. Fyy is going to be 4. And fxy is going to be 2. And now I'm going to plug in my point. But there's no x's or y's to actually plug it into, right? This thing is just always. So I'll point out that if you plug in x equal to 6 and y equal to 3, you still get 2 times 4 minus 2 squared, which is equal to 4. So what does that mean when d is greater than 0? What it really means is we need to do more work. It means we either have a maximum or a minimum. It depends on the second derivatives. So we can say that, well, since fxx is what? 2 specifically, but more importantly, it is positive. We know that we have a, I mean, what do we want to get? We wanted a minimum, right? And it is, right? Because it's concave up, so we have a minimum. So we do have a minimum. Minimum at 3,6. Sorry, 6,3. Meaning to make the duration of this infection or sickness or whatever it was, infection, we want 6 milligrams of drug 1 and 3 milligrams of drug 2. Yeah. Yes. That word. Minimize. So I see a function of 2 variables. So let's read the question here, because I do think your question is an important one. So I know it, right, and there's a lot of words here, right? I'm trying to kind of boil it down to what's necessary. So blah, 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 combination of 2 drugs is being tested, right? Okay, in order to treat a certain type of, right? There's words that are important, but kind of not that important, right? I know there's 2 drugs being tested. Studies have shown that the duration of the infection can be modeled. Okay, so here's the thing that's telling me how the infection works. And that's the duration of the infection. So this function, if I input 2 numbers, tells me how long I'm going to be sick for or infected, whatever. And I want that to be long or small, long or short. I prefer to be short, right? I don't want to be infected for, I mean, assuming that's what we want, right? So X is the dose in hundreds of milligrams, sorry, 600 milligrams and 300 milligrams, apologies. X is the dose in hundreds of milligrams, the first drug, and Y is the dose in hundreds of milligrams of the second drug. Here's the important question. What dose combination, meaning what X and Y, right, those are the drugs, of the drugs will minimize the duration of the infection or minimize the function. And as soon as I see the words minimize the function, that's when I kick into this process. I'm like, oh, find the two partials, set them equal to 0, get the critical point or points, and then test them to see if any of them are a minimum or a maximum or whatever. Fair question. Okay. Other questions about this problem? Terrible habit. And it's not that terrible, right? It's not like, I mean, there are a lot of way worse habits like smoking cigarettes, which I don't do, in case you, not that you need to know, but yeah. All right, let's do the next one. Evaluate or show the limit does not exist. All right. Well, let's look at this first one, which looks super straightforward. The limit is x comma y approaches 1 comma 1 of 6xy over x squared plus y squared. If I plug in 1, 1, do I get a real number? Like not 0 over 0? I sure do. I get 6 times 1 over 1 plus 1, which is not 0 over 0, which is 6 over 2, which is 3. Check. Done. You can just plug it in and get a real number out. That's it. That's your answer. More likely than not, you won't get a real number out. You'll get something like 0 divided by 0, probably. And when that's the case, we usually take the path, literally, of taking many paths. So the limit as xy approaches 0, 0 of the same thing, 6xy over x squared plus y squared. And I'm not even going to write it because we can all see that if you plug in 0 for x and 0 for y, you're going to get 0 divided by 0, which could be anything. Probably going to not exist because it's probably going to be different things from different directions. Here is my probably best piece of advice for working on these limits that go through the origin. Try the path. Either try x equal to 0 or y equal to 0. Those are almost always choices that will work, that will give you something, and they're usually very easy. So if I try x equal to 0, for example, so for x equal to 0, then I'm going to have the limit as y goes to 0, right? Because there's still y is not equal to 0. Y is still moving closer and closer and closer to 0 along the path x equal to 0. And on top, I'm going to have 6 times 0 times y. On the bottom, I have 0 squared plus y squared. This is the limit as y goes to 0 of what? What do I have on top? What do I have on the bottom? Y squared, which isn't 0 yet. Eventually, it's going to be 0, but eventually it's going to be too late to matter. Because what's 0 divided by not 0? 0. So before I even take the limit, I recognize that I'm taking the limit as y approaches 0 of something that's always 0. And then you get to make the easy conclusion that the limit of a constant is just the constant. So 99 times out of 100, when you pick y equal to 0 or x equal to 0, often the limit ends up being 0 because you 0 on top and not 0 on the bottom, which is nice. It's easy. Now we just have to find another path. Anyone have any suggestions? Excellent choice. And it's an exceptionally excellent choice because often trying to make the limit be something other than 0 you would really love for like all the powers in the numerator and all the powers in the denominator to be the same. And y equal to x is kind of like the primo choice for that to happen. So if we pick y equal to x or x equal to y, either way you want to say it, you can really use either one. I typically like to write it as with x's. So I'm going to replace every y with x, and look what I get. I get 6 times x over x squared plus x squared. And simplifying, I have the limit as x goes to 0 of 6x squared over 2x squared. And oh, the x squareds cancel. How lovely. And then we're left with the limit as x approaches 0 of 3, which is 3. And then we see the thing we expected to see, which is that the limits in different directions are not equal, which means the overall limit does not exist. Something to think about when you're answering a question like this, or not really think about, something to make sure you do is to write the limit in every step until you actually get to the value. It is worth a point probably or more, right? Because if you don't write the limit, it has a different meaning. And we don't want it to have a different meaning, right? We need to have a value. Yeah. Yes. So I don't know what y equals to x squared is going to be. So here's what I will say. From what we've done here, we don't need to do any more work. But let's say that we didn't remember that James said it was great to use x equals 0 or y equals 0 because we forgot the wonderful things he said. And we did this one, and then we're going to try something else. And I would, if I had forgotten about y equals 0 or x equals 0, the next thing I would probably try would be y equals x squared. So if I try y equals x squared, let's see what happens. I'm going to do the limit as x goes to 0. Let's see. So now I'm replacing the y's with x squared. So I'm going to have 6 times x squared over x squared plus x squared squared. This is not feeling so great. The limit as x goes to 0 of 6x cubed over x squared plus x to the 4th. Okay. So typically what you want to do in this situation is from the denominator, you want to pull out x to the lowest power. Meaning I'm going to factor out what from the denominator. Yeah, x squared. And when I do that, I have the limit as x goes to 0, 6x cubed over x squared times x1 plus x squared. And then I can cancel x squared there and x squared there. And then we end up getting the limit as x goes to 0 of 6x over 1 plus x squared, which is going to be 0 over 1 plus 0, which is 0. So that'll also get us to something that's different, which is good. So that would totally work. The thing is, no, there's nothing. That's the thing. It's never enough to show that 5, 6, 7, 8 different paths have the same value. If you are trying to show the limit exists, which hopefully you don't have to show, it's probably going to be one of those squeeze theorem kind of deals. Where you have to be like, oh, this thing is less than this other thing, and it's going to 0, and it's bigger than 0, which is also going to 0. How many tasks should we test minimum? Good question. As many as it takes to show that it doesn't exist is really the answer. Or if you've done like 4, yeah, usually when I get to 4, I'm like, okay, maybe it exists. Then that's when you have to start thinking about trying to do some sort of probably squeeze theorem kind of thing. Okay, which we can talk about in a second if we need to. What time is it? Okay, we got enough time. Yeah, maybe. Okay, better step it up here. Let's do this next one. The limit as x, y approaches 0, 0 of xy squared over x squared plus y to the fourth. Okay. And again, I'm going to take the path of least resistance, meaning the path of 0. So I'm going to let y equal to 0. And I'm going to have the limit as x approaches 0 of x times 0 over x squared plus 0 to the fourth, which is the limit as x goes to 0 of 0 over x squared, which is the limit of 0, which is 0. So now I just need to find another path where the limit's not 0. And I'm pretty sure that y equal to x is not going to work out so well. So if I pick y equal to x, let's just think about what happens. If I pick y equal to x, I'm going to get x cubed on top and x squared plus x to the fourth on the bottom. And well, it's really almost the same thing we had before, but if you factor out an x squared from the bottom, I'm going to have an x left on top, which is going to go to 0, and a denominator that's not 0, that's going to be 0 as well, which isn't bad. It's just not helpful because that's not a different value. So what do you guys think might be a better path where I get the kind of thing that I said I wanted to have? I would really love to make a choice where the powers on the highest, all the powers on top and all the powers on the bottom end up being the same. I think that's the choice I want. You could also do y equal to the square root of x, but I will tell you, if you ever have the option of picking a root versus a power, pick the power. Right? Y equals root x is kind of the same as x equals y squared, but x equals y squared doesn't have any domain problems. It's the better choice. So pick this, not this. Because this is defined for all x and y. This is not. Okay, so then we get the limit as x goes to, sorry, as y goes to 0, because I'm replacing all the x's with y's, of y squared times y squared over y squared squared plus y to the fourth. Oh, that's going to work out great. I'm going to get y to the fourth on top over y to the fourth plus y to the fourth, which is 2y to the fourth. And then those cancel, and you get the limit as y goes to 0 of 1/2, which is 1/2, which is not 0. So this limit does not exist. Oh, yeah, that problem's good. So, oh, you guys can see it. Here is the next problem, which is a little bit of a tough one. A flat circular plate has the shape of the region x squared plus y squared less than or equal to 1, which is just the circle. I really should say it's the disk of radius 1, right? Because you're including all the points inside it. If it's x squared plus y squared less than or equal to 1, that's a plate, circular plate. The plate is heated so that the temperature at any point xy is given by capital T of xy equals x squared plus 2y squared plus x. Find the hottest and the coldest points. So this is very much a problem like we were doing last class, except it's a little harder actually. It's a problem where we're going to find what's happening at any critical point or the temperature at any critical point. And then we also have to think about the boundary, because maybe it's coldest at the boundary point or hottest at the boundary point, right? We don't know if like it's getting really, really cold and it just stops because there's your boundary. So let's write some stuff down. We have this. And then our temperature is given by x squared plus 2y squared plus x. Okay, this one's extra tricky, I'm not going to lie. So first, let's find our critical points. And something to remember, when you're dealing with this sort of thing where you have a limited region or a limited domain, your critical point, if you want it to, if you actually end up testing it, it needs to have been in the domain. Right? If I end up getting like 5, 0 as a critical point, it's out because it's not in the circle of radius 1. So partial with respect to x is 2x plus 1. Partial with respect to y is 4y. Set this equal to 0, and you get x equal to -1/2, y equal to 0. So -1/2 comma 0, which is definitely in the circle of radius 1, is our critical point. It's where the plate might be the hottest, the plate might be the coldest. It can't be both though, unless the plate is the same temperature everywhere, which it's not. So then, and this is where this problem is hard, then we have to consider the border. But unlike the problems where you have like a rectangle or a triangle or a square, you can't just be like it's y equals 4 and y equals 0 and x equals 1 and x equals 3. What do we do? This is where we have to parameterize. Let me look at my notes here. Like so what we typically do for this is we say, oh, if you're on a circle, we're going to let x equal cosine of t and y equals sine of t. Because for any t, that point is on the circle. Right? If t is 0, cosine of 0 is 1, sine of 0 is 0. Or if t was pi over 2, you'd be up there. So literally, that gives us the entire border. Then what we're going to do is we're going to go back and plug that into the, I think no, this is right, check something. We plug that back into the original function, yeah. So now we're going to write temperature as a function of little t, and it's going to be cosine squared of t plus 2 times sine squared of t plus cosine of t. And I guess we can make our lives easier. In fact, I might have done this before even, yeah, it might have been smart to see that this is x squared plus y squared plus y squared plus x. And if we're on the circle, what's x squared plus y squared equal to? Or we could see it here. We could say, look, hey, James, I see that I have a cosine squared of t plus 1 sine squared of t plus another sine squared of t plus cosine of t. You can be like, I know that cosine squared t plus sine squared t is always equal to 1. That's equally, it's really the same thing, just seen differently. The point I'm trying to make is I want to make my life easier before I differentiate. It's less work to differentiate 1 plus sine squared plus cosine than it is to differentiate all of that. Not a lot less, but enough that it's worth looking at. So now we're going to find the derivative. So the derivative of 1 is 0. What's the derivative of sine squared? Well, it's not cosine squared, right? Because really this is some stuff squared. And the derivative of some stuff squared is 2 times my stuff to the first times the derivative of the stuff. So it's 2 times sine times cosine. And then the derivative of cosine of t is negative sine of t. And that has to equal 0. Oh, that looks kind of complicated. I mean, not super complicated, but a little. So then I'm going to factor out a sine. I've got sine of t. I'm left with 2 times cosine of t minus 1. All right. So on my plate, t, the angle, could either be, well, t could be 0. T could be pi, because sine of pi is also 0. T could be pi over 3, because cosine of pi over 3 is 1/2, and 2 times 1/2 minus 1 is 0. Or it could be over in quadrant 4, 5 pi over 3. These two values come from setting sine of t equal to 0. These two values come from setting cosine of t equal to positive 1/2. It's a little tricky. And then we finally have all our points. Well, kind of. We have this point here. And then we could go back and plug these into cosine and sine to find the corresponding x and y values. So here are our points. we have xy equal to -1/2, 0. And then for t equal to 0 and xy equal to cosine comma sine, cosine of 0 is 1, sine of 0 is 0. For t equal to pi, cosine of pi is -1, sine of pi is 0. Or for t equal to pi over 3, cosine of pi over 3 is 1/2, sine of pi over 3 is √3/2. And finally, for 5 pi over 3, which is in quadrant 4, sorry, can you see that? No, you can't. Cosine of 5 pi over 3 is 1/2. Cosine of 5, sine of 5 pi over 3 is -√3/2. So these are the values we have to plug back into our function, x squared plus 2y squared plus x, to see where this thing is the hottest and where this thing is the coldest. Do I think this is a good exam problem? It's maybe a little over at the edge. But I have definitely seen people ask questions like this. So maybe. I think a better question would be one where we didn't have to do this parameterizing thing, which we can do if we have time. So plugging this back in, capital T at -1/2, 0 is going to be 1/4 plus 0 minus 1/2, which is -1/4. Capital T of 1, 0 is going to be 1 plus 0 plus 1. Capital T of -1, 0 is going to be 1 plus 0 minus 1. Capital T of 1/2 comma √3/2 is going to be 1/4 plus 2 times 3/4 plus 1/2, which is gross. It's 6/4 plus 1/4, which is 7/4 plus 2/4, which is 9/4. And finally, this one actually gives you the same value, because you get 1/4 plus 2 times still positive 3/4 plus 1/2. I didn't circle that one for any good reason, other than I was just circling the first one, but it actually does happen to be the minimum value. So that is the least value. And these are both the most values. So the plate is the hottest at these points. Hot. And the plate is the coldest at this point. But I do think a better question, or maybe not a better question, but maybe an easier, no, I don't even know if easier is the right word. A different question would be to ask this question, but instead of having the circular region, have a triangular region, which it isn't going to be that much more work. So let's go ahead and do that one as well. Because I feel like he's definitely going to ask you a question in some sort of vein like this, where you have like a limited domain, right? We've done homework problems on it. It feels like it should be on the test. So let's look at this follow-up, part B here. Okay. So part B, same function, same critical point of -1/2 comma 0, but now the domain we're looking at is between the points, the triangle between the points, 1, 1, -1, 1, and -1, -1. Great, this is not so terrible. You might think it's terrible, but it's not. So we have to check our corners. So we're going to check T of -1/2, 0, that's our critical point. And then we're going to do the thing evaluated at each corner. And then what else do we still have to worry about? To the windows, to the walls, not the rest of the song. So anyway, we have to worry about the walls. We have the wall here, y equals 1. We have the wall here, x equals -1. And what's this last wall? That goes from the point -1, -1 to the point +1, +1. Yeah. So we're going to use each of those. So for x equal to -1, we're going to plug in x equal to -1 and get t of y equals 1. I don't think you need to bring graph paper to the exam, but if you can have extra paper, you certainly could bring it. But it shouldn't be, they should give you a picture. It shouldn't be super hard to graph. So t of y is going to be, sorry, t x is -1, you get 1 plus 2y squared minus 1. I don't even really care about those constants. Yeah, they cancel out, but their derivative is going to be 0. I'm not even going to take the time to cancel them. I'm just going to, oh yeah, t prime of y is going to be 4y, set that equal to 0. You get y equal to 0. So I'm getting the point -1, 0. Right? X is -1, y is 0. And then I'm going to do for y equal to 1, t of x is going to be x squared plus 2 plus x. And the derivative is going to be 2x plus 1 equal to 0. You get x equal to -1/2. So -1/2 comma 1 is another point. And then finally, for y equal to x, doesn't matter which one you choose to pick. I usually use x's if I'm going to use one of the variables. I mean, x squared plus 2x squared plus x. That's 3x squared plus x. And then the derivative is 6x plus 1 equal to 0. So x equals -1/6, which is still in the domain, right? So, oh, and what's y going to be? What's y going to be? Right, we're on the wall where y equals x. So if x is -1/6, y is -1/6. How do you know if your plane will be a plane, a circle, triangle? I don't have the ability to type it right this moment, but I can try typing something at the end. Sorry, your headphones are not working. I apologize. Not that it's my fault, but still, I'm sorry. So plugging this in. So this is kind of the grunt work part of it. I don't think it's super necessary for us to, like as he tries to get out of doing the work. So we already know what this one's going to be. 1/4 minus 1/2, which is -1/4. Plug in 1, 1, we get 1 plus 2 plus 1. Plug in -1, 1, we get 1 plus 2 minus 1. -1, -1 is going to be 1 plus 2 minus 1. -1, 0 is going to be 1 plus 0 minus 1. -1/2, 1 is going to be 1/4 plus 2 minus 1/2, which is 2 minus 1/4, so 1.75 or 7/4. And then this one is ugly. It's going to be 1/36 plus 2/36 minus 1/6, which is 3/36 minus 6/36, which is -3/36, which is -1/12. All right. Which one's the biggest? 4, the biggest. Which one's the smallest? Well, there's 2 candidates. Which one is smaller? That one. It's more negative, right? Because it's a bigger fraction. If you think about fractions, 1/4, a quarter of something, is bigger than 1/12, a 12th of something. And so -1/4 is more negative than -1/12. Bigger denominator, smaller fraction. And so I want the most negative thing. Oh, -1/4 is the most negative thing. Okay, I think we can get through the rest of this. All right. Number 5. I should try to cycle through these pens so I don't just kill one right away. Find the domain and range of f of xy equal to 6 over the square root of 9 minus x squared minus y squared. Also describe the level curves. So domain. I see a denominator. I see a square root. I know I can't divide by 0. I know I can't take the square root of a negative. So what I need is for that stuff inside the square root that's also in the denominator to be strictly greater than 0. If it was just the square root in the numerator, I'd take it to be greater than or equal to 0, but it's not. I see an x squared plus y squared. So I'm going to rewrite this as 9 bigger than x squared plus y squared. Or if you prefer, x squared plus y squared less than 9. If I was asking this question on a test, I would probably ask my students to be like, hey, can you graph the domain? Like, sure thing. It's a circle of radius 3, but not including the boundary. Because it's not less than or equal to. Is it everything inside the circle or outside the circle? If you're not sure, test the point. What's an easy point that's inside the circle? The origin, right? Like, I mean, there's other points, sure, but the origin. If x is 0 and y is 0, is this inequality true? Yes. So 0, 0 is in the domain, and then everything that's on that side of the border is in the domain. And if you're curious, I would point out that this domain is open and bounded. Bless you. Bounded because x and y can't be as large as you want them to be, right? They're limited in their scope. And open because we do not include the boundary. So something is typically closed if the boundary is included. It's typically open if the boundary is excluded. And if you've got some of it, then it's neither, which is annoying. There's a more formal definition of closedness and openness, but I think for the intents and purposes of this class, knowing that closed is essentially we include the border, open is essentially we exclude the border is sufficient. Range is a little bit harder, but not impossible. Itchy nose, okay. So I've got this, but I've got something else as well. I know, and in fact, let's start with this. Yeah, that's good. Let's be smart about this. Or let's start with this. Here's what we know. We know this for sure needs to be true because that's our domain. And then I know you guys know this. What does x squared plus y squared have to be bigger than or equal to? I know you know. Right? It's got to be bigger than or equal to 0 because it's positive. Actually, I should say it's non-negative, right? Because x and y could be 0. But any choice for x and y gets you non-negative results if you square them and add them together. Well, that's going to help us because now we're going to make this look like that. If I know that x squared plus y squared is between 0 and 9, I also know that 9 minus x squared plus y squared is between 0 and 9. Except it's switched. I know I did a couple steps there that I didn't actually show. What you could really do is multiply everything by -1 and then add 9 to everything. But really, if the biggest this can be is 9, well, not quite 9. If you do 9 minus it, the smallest it can be is almost 0. And if the smallest this can be is actually 0, then the biggest 9 minus it can be is 9 minus 0. And then square roots abound. Why did I write the square root of 3? Because I was not being careful. And then we're going to take the reciprocal of everything. So 1/3 is less than or equal to 1 over the square root of 9 minus x squared minus y squared is less than 1 over 0. Let's just say infinity. Right? If something is bigger than 0, its reciprocal can be really any positive number. I'm going to say that again, right? This number here is bigger than 0. It can be very, very large when you take the reciprocal of it because essentially we're saying this gets really, really, really close to 0. And so its reciprocal is really, really, really big. And then finally, multiply everything by 6. Now 6 times infinity is still infinity. So here's what we've got for our range. The range is bracket 2 to infinity. Which makes sense if you look back at this original function, right? If you just think about it for a second, the smallest that can be is when the denominator is as large as possible. And the largest that denominator can be is 3. There's no way for the denominator to be bigger than 3. I can't make that the square root of anything larger than 9 in there because I'm always subtracting stuff off of it. So that's why you have that. And then this can be as large as you want it to be by making the denominator very, 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 very close to 0. What are the level curves? How do you find level curves? To find level curves or to think about the level curves, you want to set the whole thing equal to some constant. Sometimes we use C, sometimes we use Z. Let's use C. I am expecting some sort of circle. I'm going to multiply both sides by the denominator and divide both sides by C. So the 6 over C is the square root of 9 squared minus x squared minus y squared. And then square both sides. And then add x squared plus y squared over here. Subtract 36 over c squared over there. That looks like a circle to me. So my level curves are circles with the radius as, and this is where things are kind of crazy, the square root of that number over there. If someone wanted to be very specific, like they often are on web work, which I know you aren't doing for this class, but sometimes they would say the level curves here are circles that are not spaced apart equally, because each time you increase C by 1 or more, you don't get the same amount of increase in your radius. And then the last thing I should say is it should be noted here that your level curve values have to be in the range. So note, C needs to be bigger than or equal to 3. 2 or 3? 2, apologies, right? Our range was 2, not 3. Sorry about that. Right, if C is 1, you're going to have problems. 9 minus 36 is negative. If C is 2, you're fine. 9 minus 9 is 0. If C is bigger than 2, great. 6 minutes. Yeah, we can do this last problem. Although, to be honest, I feel like he didn't really ask you a lot about problems like this last one, but it feels like such a typical problem that I feel like we should talk about it anyway. So we'll do this last one. 6a, sketch level curves on the same set of x, y axes for f of xy equal to x squared minus y for z equal to -1, 0, and 1. Okay, so all we're going to do is we're just going to set the function equal to these values and then sketch the curve. So for z equal to 1, we're going to have x squared minus y equal to 1. I would much rather solve for y, right? X squared minus 1 equals positive y. I know how to graph that. It's a parabola shifted down 1. And for z equal to 0, x squared minus y equals 0 is going to become y equal to x squared. Great. For z equal to -1, x squared minus y equals -1. So we're going to get x squared plus 1 equal to y. Well, good. I can graph those parabolas relatively decently. So if I were trying to make this look somewhat nice, I might plot a couple extra points. Specifically, I know that when I plot a like normal parabola, like I get the vertex. So for this first one, like, or for this last one, y equals x squared plus 1, the vertex is right there. And then the next points are over 1 and up 1. So I'm going to get the point 1, 2 and the point -1, 2. And then I just try not to screw it up. Good approach to most math classes. Just try not to screw it up. And then if you are drawing level curves, you should label them. So this one here was this one here. So that's when z equals -1. And then I'm going to draw the level curve for z equals 0. So I can point the vertex 0, 0, and then the points are 1, 1, and -1, 1. Now something to be aware of. The level curves should not cross each other. At least not usually. I can't think of a time when they do, but I could be mistaken, but No, I guess that, yeah, you can have level curves cross each other. I take it back. They could cross each other. It just doesn't, we usually don't look at examples where they cross each other, to be totally frank. And then finally, y equals, oh, and that's, sorry, that's z equals 0. And the last one here, when z equals 1, shift it down 1 again. So there, and then we get that point. If you're allowed to use multiple colors on your test, if you have to draw level curves, I would encourage you to do so because it makes it easier for them to see which one's which. There are my level curves. And now here are some not terrible questions to answer. Okay. Based on, oh, sorry, plot the point 1, 1, 0 on your contour plot. Okay, so x is 1, y is 1, and z should be 0, which it is because I'm on the 0 level curve. So that's the point 1, 1, 0. Great. Based on your plot, is the function, so this is where my thing got cut off, is the function increasing or decreasing in the x direction? So if we move in the x direction, which is which way? Left, right, up, down? To the right. Specifically, when they say in the x direction, they mean in the positive x direction. So we move in the x direction. Is the function getting larger or smaller? Larger, right? Because the level curve is a bigger value. We're going from a function value of 0 towards a function value of 1. So in the x direction, the function is increasing. In the y direction, the function is, well, if we move upwards, we're going towards a smaller value, right? The function value is less. So the function is decreasing. No, that's 6b, sorry. And then the last part of this question, which also got cut off, was find the partial derivatives at that point and verify that the thing we said was true before is actually true. Meaning, if we find the partial derivative in the x direction at the point 1, 1, it should end up being positive because we said that the function is increasing at that point in that direction. Okay, well, that's not too bad to find. If I find the partial derivative, it's going to be 2x evaluated at x equal to 1, y equal to 1, which is going to be 2, which is positive, which means, oh yeah, the function is increasing in that direction. And similarly, fy evaluated at 1, 1 is, well, the derivative of x squared minus y is just -1. And then even have a place to plug in the points. You just get -1, which is certainly negative, which means the function is decreasing. I really should say increasing in the x direction, decreasing in the y direction.